Imagine walking across the surface of a diamond planet, black skies above you, diamond crust beneath your feet. Every step echoes faintly through crystal ground, a sound sharp, clean, eternal. And as you move, it dawns on you. The very floor beneath you would be considered priceless on Earth. Every step would shatter our sense of value, because here, diamonds aren't treasures. They're terrain. What would precious even mean on a world made of jewels? Somewhere beyond the reach of our telescopes, such worlds might exist. Stranger than anything we've ever seen. Not rocky like Earth. Not gaseous like Jupiter. Not frozen like Neptune. But built almost entirely from something we call rare. Diamond. Picture a planet whose mountains shimmer under a dim sun, whose crust gleams faintly in starlight, where the bedrock itself is crystalline, harder than anything on Earth, older than anything we've ever touched. It sounds like a dream, but in the language of astrophysics, it may be a perfectly ordinary reality. What if entire worlds were made of diamond? It's a question that blurs the line between science and poetry, because to understand it, we have to let go of human value, the idea that diamonds are beautiful because they're scarce. In the universe, beauty isn't measured in worth, it's measured in chemistry. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, the strange and the beautiful that the universe hides in plain sight, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow and it keeps these journeys alive. Now, let's stay with that image for a moment. A world of diamond. Its mountains shimmering under a dim sun, its crust gleaming faintly in starlight. A place where the bedrock itself is crystalline, harder than anything on Earth, older than anything we've ever touched. It sounds like fantasy, but in the language of astrophysics, it might be a perfectly ordinary reality, because the universe doesn't share our sense of value. It doesn't deal in rarity, only in chemistry. Every world, every moon, every drifting grain of dust is built from ratios. The balance of carbon, oxygen, silicon, hydrogen. Those quiet equations decide everything a planet will become. Our world, Earth, is what astronomers call oxygen-rich. That one fact shapes everything about it. Most of our carbon was locked away early, bound to oxygen as carbon dioxide. What remained went into life, and the rest into stone. The result is a planet of silicates. Quartz, feldspar, olivine. Minerals of oxygen and rock. But tilt that balance, make carbon more abundant than oxygen, and the recipe changes completely. Oxygen bonds with carbon to form carbon monoxide, leaving the excess carbon free to build solids. Instead of silicates, you get carbides, compounds of carbon and metals, instead of granite silicon carbide, so hard it can grind diamond here on Earth. And deeper below the surface, under unimaginable pressure, carbon atoms could crystallize into diamond, not as gemstones, but as geology. These are the carbon planets, or as some call them, diamond worlds. The idea first appeared in the early 2000s when astrophysicists Mark Kuchner and Sarah Seeger proposed that planets forming around carbon-rich stars could end up made largely of graphite, carbides and diamond, because stars, like people, are not all the same. Some, like our Sun, are oxygen-rich. Others, called carbon stars, are older and cooler, filled with the ashes of nuclear fusion. As they die, they exhale carbon into space, enriching the nebulae around them. And when that carbon-to-oxygen ratio climbs above 1, chemistry itself rewrites the rules. In those systems, almost all the oxygen is trapped in carbon monoxide gas. The leftover carbon bonds with silicon, iron, and titanium, and from that mixture, dark, glittering worlds are born. Their crusts could be graphite, their mantles diamond, layers stretching thousands of kilometers, thousands of miles deep. To put that in perspective, on Earth, diamonds form roughly 150 to 200 kilometers, 90 to 120 miles, beneath the surface, where pressures reach about 45 to 60 kilobars and temperatures rise above 1000 degrees Celsius, 1830 degrees Fahrenheit. But in a carbon planet, that pressure would exist everywhere below the crust. Entire mountain ranges could be carved from solid diamond. It's strange to think that what we see as rare could be utterly common elsewhere, that the universe might scatter diamonds like dust across the stars. Our telescopes have already revealed worlds that rain molten glass, planets that orbit so close to their stars their surfaces glow red hot, and others covered in metallic clouds. So a planet made of diamond isn't even the strangest possibility. One of the most promising examples sits just 8.6 light-years away, 55 Cancri A. A rocky world about 8 times heavier than Earth, orbiting its star in only 18 hours. Its density and the carbon-rich chemistry of its host star suggest it could contain an immense diamond mantle beneath a molten crust. Imagine standing there, on a horizon sharp and black, the ground dark as graphite, glinting in the orange light of a nearby sun. No oceans, no clouds, no blue, only silence, heat, and crystal. And when the light fades, the planet disappears, a world of endless diamond swallowed by darkness. That's the strange poetry of the cosmos. It creates unimaginable beauty where no eyes will ever look, a billion carats glittering in silence, and no one to care. Maybe that's the quiet truth behind diamond worlds. That value depends on perspective. On Earth, we tear open mountains to find a single gem. Elsewhere, whole planets are built from them, and no one keeps count. A diamond the size of a planet isn't priceless. It's just physics, pressure, temperature, and time. And somewhere, in the cold between the stars, another carbon world is forming right now. A dark sphere cooling slowly, waiting for light. When that light finally touches it, for a fleeting moment it will shimmer, and then fade again into shadow. That's where our story begins. When we look at the night sky, we often imagine the planets circling distant stars as reflections of our own, worlds with oceans, skies, and familiar elements. But in truth, every planet begins as nothing more than dust, tiny, silent grains drifting through the nebula left behind by dying stars. Each of those grains carries a cosmic inheritance, the ashes of supernovae, the carbon from red giants, the oxygen and silicon forged in ancient stellar cores. And as they swirl and collide, drawn together by gravity's patient pull, they begin a kind of planetary alchemy, the slow transformation of elements into landscapes, into mountains, into worlds. What a planet becomes depends entirely on the ingredients it starts with, and the key, perhaps more than any other factor, is the ratio of carbon to oxygen. On Earth, and in most of the known planets orbiting other stars, that ratio tilts heavily toward oxygen. For every carbon atom, there are nearly 2 atoms of oxygen. It's a quiet imbalance, but it decides the fate of everything. In an oxygen-rich environment, almost all the carbon bonds quickly with oxygen to form carbon monoxide or carbon dioxide gas, the same gases that shape our own atmosphere. That leaves silicon and other elements to combine with what oxygen remains, forming silicates, the family of minerals that make up nearly all the solid crust of Earth and other rocky worlds. Silicates are everywhere here. Quartz in sand, feldspar in granite, mica in dust. They're the unremarkable scaffolding of our planet, and yet they owe their existence to a small numerical detail written into the chemistry of our solar system 4.5 billion years ago. Our Sun, and therefore our solar nebula, contained roughly twice as much oxygen as carbon. It's that ratio, written in the very dust from which Earth formed, that ensured our planet would be blue and silicate-rich instead of black and carbon-heavy. But what happens when that balance shifts? What if, in some other region of the galaxy, the ratio flips, when carbon becomes more plentiful than oxygen? Then everything changes. In a carbon-rich protoplanetary disk, oxygen is quickly locked away as carbon monoxide, leaving little free oxygen to build silicates. Instead, carbon takes charge. It bonds with metals and silicon to form compounds like titanium carbide, silicon carbide, and iron carbide, all materials harder, darker, and denser than the rocks beneath our feet. The geology of such a planet would be unrecognizable to us. Its crust might be rich in graphite, the same form of carbon found in pencil lead, with mountains and plains made of dark metallic minerals. Beneath that crust, under pressures that could reach hundreds of kilobars, layers of carbon would compress into solid diamond, forming an enormous crystalline mantle extending for thousands of kilometers. It's a kind of planetary inversion. A mirror image of our own world, sculpted not by oxygen, but by carbon. Where our mountains are granite and basalt, theirs would be carbide and crystal. Where our volcanoes spill molten silicate rock, theirs might ooze metallic carbon compounds. Where our clouds shimmer with water vapour, theirs could glisten with methane or acetylene. This, at its heart, is planetary alchemy, the universe's own version of transformation, not by magic, but by ratio. To understand it, let's imagine the earliest moments of a solar system's birth. A star forms first, collapsing from a cold cloud of hydrogen, helium, and dust. Around it, the leftover material flattens into a glowing disk, the protoplanetary disk. Temperatures near the young star can exceed 2,000 degrees Celsius, 3,600 degrees Fahrenheit, hot enough to vaporize rock. Farther out, beyond the furnace, temperatures drop and dust begins to condense. Every substance has a condensation point, a temperature where it can shift from gas to solid in the vacuum of space. For oxygen-rich systems like ours, silicate minerals condense first, forming tiny grains of olivine and pyroxene, greenish crystals that will one day make up asteroids, planets, and moons. But in a carbon-rich disk, carbon itself becomes the dominant solid. Graphite and carbides begin to condense instead, forming grains as black as soot and as hard as stone. These grains clump, collide, and merge, snowballing into planetesimals, and eventually into full worlds. A new planet is born, not of silicate dust, but of carbon ash. It's almost poetic to think that the universe's most basic chemistry can lead to such opposites. Two planets, equally old, equally massive, built from the same cosmic dust, and yet utterly unlike each other. One green and blue, soft and weathered. The other black and gleaming, dry and eternal. But that contrast doesn't end at the surface. Even deep inside, carbon worlds would behave differently from ours. Earth's interior is layered, a thin crust, a silicate mantle, and a metallic core of iron and nickel. In a carbon planet, the structure would shift dramatically. The outer crust might be graphite, brittle, dark, conductive. Below it, as pressure rises beyond 45 to 60 kilobars, graphite would transition into diamond, forming a vast mantle of crystalline carbon. The deeper layers could mix with metallic carbides, and at the very center, a core of molten iron and carbon alloy, a kind of cosmic steel. The density, gravity, and even the way sound travels through such a planet would differ from anything we know. It might have fewer volcanoes, since carbon compounds don't melt the same way silicates do. Its crust might be far more stable, a quiet, glimmering desert under a dim red sun. For years, carbon planets were considered purely theoretical, mathematical curiosities. But slowly, evidence began to emerge that the chemistry of the cosmos allows them. Astronomers began to notice that not all stars share our sun's composition. Some, like HD 108874 and WASP-12, show strong signatures of carbon in their spectra, light absorbed at specific wavelengths that reveal the elements present in a star's outer layers. These carbon-rich stars could host entire families of carbon-dominated planets. Even our own galaxy's population hints at this diversity. In regions near the galactic center, stars tend to be more metal-rich. And metals in astronomy simply mean any element heavier than helium, including carbon. It's likely that carbon planets are more common in these inner, older regions of the Milky Way, invisible to us now, but quietly orbiting in the dark. When astronomers first modelled these possibilities, they realised that such worlds might be both common and hard to detect. Their surfaces, dark and non-reflective, would absorb most of the light falling on them. Their atmospheres, dominated by methane or carbon monoxide, would make them appear black even when close to their stars. From afar, a diamond planet would look less like a jewel and more like a shadow. But deep within that darkness, there would be beauty beyond imagination. If you could somehow slice through a carbon planet, its layers might look like the inside of a gemstone, alternating bands of graphite and diamond shimmering under theoretical light. In the upper mantle, the temperature could reach 2,000 degrees Celsius, 3,600 degrees Fahrenheit, hot enough to keep portions of the diamond mantle in plastic flow, slowly shifting and reforming over geological time. Below that, at the core, molten iron might circulate, generating magnetic fields like Earth's, though weaker and more erratic. In short, these planets would be real. Not fantasy, not myth, but the inevitable outcome of chemistry taken down a different path. When scientists first presented the concept of carbon planets, they weren't driven by dreams of riches, but by curiosity, by the question of how much variation the universe allows. If you tweak a single ratio, the amount of carbon versus oxygen, you don't just change a planet's atmosphere. You rewrite its geology, its colour, its potential for weather, and perhaps even its chance for life. That's the quiet miracle of it all. From the same ingredients, the cosmos can cook 1,000 different recipes. And yet, there's something faintly ironic here. The element that defines all life on Earth, carbon, could also create worlds utterly inhospitable to it. On our planet, carbon builds molecules, DNA, proteins, sugars. On a carbon planet, it builds crystals. It's a reminder that nature doesn't play favourites, it simply follows the rules. And those rules are astonishingly simple. When carbon wins, oxygen loses. And when oxygen wins, carbon is chained in gas. Between those two outcomes lie two completely different kinds of worlds, one blue and alive, the other black and unyielding. It's humbling to realise that everything we know about habitability may be an accident, the result of one element slightly outnumbering another in a cloud of dust billions of years ago. If our solar system had formed in a carbon-rich region of the galaxy, we might not be here to talk about it. There would be no oceans, no breathable air, no green plants feeding on carbon dioxide. Instead, there would be black skies, metallic rain, and continents of diamond glittering under a dying sun. A world beautiful beyond words, and completely dead. Still, the thought of it stirs something in us. Maybe it's because diamond worlds remind us how fragile our own balance is, that life, with all its complexity, depends on chemistry being just so, that if the universe had shifted its recipe by even a fraction, Earth might have been a planet of shining stone instead of breathing forests. And perhaps, in that contrast, there's something profoundly peaceful. The realization that our planet's fragility is exactly what makes it rare. Because somewhere, right now, there may be countless carbon worlds orbiting red stars, beautiful, eternal, and silent. Their surfaces glitter faintly in alien light, their interiors solid diamond from crust to core. They are proof that even without life, the universe still creates beauty. But their beauty is one of stillness, a kind of cosmic perfection without motion, without growth, without decay. They are, in a sense, the purest form of matter turned inward, carbon made eternal by pressure and time, and all of it decided by a single ratio how much carbon a star carried, and how much oxygen it left behind. That's planetary alchemy, not magic, not myth, but chemistry, written in the dust between stars. Every world begins in chaos. Not in silence, but in fire. Long before there were planets, there were stars, the great engines that forge the raw materials of everything. They are the universe's furnaces, where hydrogen and helium, the simplest of gases, are squeezed and burned into heavier elements. Carbon, oxygen, silicon, iron, the ingredients for everything solid. But the story of a diamond planet begins with a very particular kind of star, one that favours carbon over oxygen. In the beginning, both carbon and oxygen are born inside stars of roughly the same size as our Sun. As those stars age, they expand into giants, their outer layers cooling and reddening while their cores continue to fuse helium into heavier elements. At a certain stage, called the asymptotic giant branch, something remarkable happens. Convection currents inside the star carry freshly forged carbon from its hot core to its cooler surface. The star begins to exhale carbon into space, enriching its surrounding nebula. These dying stars, often red and bloated, are called carbon stars. Their light has a deep crimson hue, and their atmospheres shimmer with carbon compounds, tiny grains of soot and graphite floating in the stellar wind. Some of that dust will drift off into the galaxy, cooling and coalescing into new clouds of gas, the raw material for the next generation of solar systems. If the ratio of carbon to oxygen in that cloud, the C/O ratio, exceeds 1, then chemistry itself takes a new path. Oxygen becomes the limiting ingredient, consumed by carbon monoxide, while the leftover carbon bonds with metals and silicon to form compounds that simply don't exist in oxygen-rich environments like ours. That's the seed of a carbon world, a planet born from the ashes of a carbon star. But not all carbon-rich environments come from dying red giants. Some are born from far more violent stars, Wolf-Rayet stars. Wolf-Rayet stars are among the hottest and most massive known. They burn through their nuclear fuel at furious speeds, shedding their outer layers through powerful stellar winds. In the process, they expose their inner cores, rich in helium, carbon, and oxygen. The material ejected from these stars floods the surrounding interstellar medium with heavy elements, including vast amounts of carbon dust. A single Wolf-Rayet star can lose the mass of our Sun in less than 1 million years, blowing carbon compounds into space faster than most stars can form them. And when such material mixes with interstellar gas and collapses under gravity, it forms new solar systems enriched with carbon, the perfect environment for diamond worlds to take shape. So what happens next? In these newborn systems, a protoplanetary disk forms, a swirling, flattened ring of gas and dust orbiting a young star. Within this disk, temperatures and pressures vary dramatically. Close to the star, heat dominates. Farther out, cold reigns. At distances where the temperature drops below roughly 2,000 degrees Celsius, 3,600 degrees Fahrenheit, solid particles can begin to condense from gas. But what condenses depends on chemistry. In our solar system, rich in oxygen, those first solids were silicate minerals, olivine, pyroxene, magnetite, the ingredients of ordinary rock. But in a carbon-heavy disk, the condensation sequence is reversed. Instead of silicates, carbides and graphite are the first solids to form. Astrophysicists have modelled these reactions, and the results are astonishing. At high temperatures, titanium carbide and silicon carbide form first, both black, crystalline, and nearly indestructible. As the disk cools, graphite condenses, carbon arranged in flat sheets, slippery and metallic grey, and deeper within growing planetesimals. As gravity increases pressure, those graphite layers begin to transform into diamond. It's not an instant process. Planetary formation is a slow, turbulent ballet. Dust grains collide and stick together electrostatically, forming clumps a few millimeters wide. Over thousands of years, those clumps become boulders, then mountain-sized planetesimals. Each collision adds mass, heat, and compression, the ingredients needed to reshape matter from soft dust into solid rock. Inside those growing bodies, temperatures may rise above 1,200 degrees Celsius, 2,200 degrees Fahrenheit, from the kinetic energy of impacts. At depths of several hundred kilometers, a few hundred miles, Pressures can climb past 45 kilobars, enough to force graphite to rearrange into diamond. In time, the interior becomes a patchwork of minerals, carbide at the surface, diamond beneath, and metal alloys at the core. What's remarkable is that this transformation, graphite to diamond, doesn't require magic or even extraordinary conditions. It's simply the natural outcome of carbon-rich material under gravity. In that sense, every carbon planet is a cosmic pressure cooker, one that turns dust into gemstones on a planetary scale. To visualize what these planets might look like from the inside, imagine slicing one open. The outermost layer would likely be a thin crust of graphite, soft, dark, reflective. Graphite's flaky structure makes it a poor building material, but an excellent conductor of electricity and heat. If lightning or tectonic activity existed there, it might dance across the surface in strange, luminous filaments, leaping through sheets of carbon crystal. Beneath that lies the mantle, where diamond takes over. At pressures exceeding tens of thousands of kilobars, carbon's atoms pack tightly into a lattice, forming the hardest material known. This mantle could be thousands of kilometers, thousands of miles, thick, extending almost to the planet's core. And at that core, a mixture of iron, nickel, and carbon might form a dense metallic heart. A liquid ocean of molten alloy, perhaps generating a weak magnetic field. It's not hard to see why such a world might survive for billions of years with little change. Diamond conducts heat efficiently, which means the interior would cool slowly, reducing tectonic activity. Without plate movement or volcanoes to renew the surface, the planet might remain geologically frozen, an unchanging monument of crystal and metal. If one could stand there, if standing were even possible, the landscape would be alien beyond comprehension. The surface might appear as a smooth, glassy plain of graphite, interspersed with reflective cliffs of carbide rock. In places, meteor impacts could have cracked the crust, revealing bright flashes of diamond beneath, the raw interior glittering like buried stars. The temperature might swing wildly depending on its orbit, blistering near 1,500 degrees Celsius. 2,700 degrees Fahrenheit on the day side, dropping below freezing on the night side. And yet, despite the violence of its birth, such a planet would be calm now, inert, silent, and shimmering. When scientists attempt to simulate these worlds, they rely on both spectral modelling and high-pressure laboratory experiments. We can't yet visit a carbon planet, but we can recreate their chemistry in miniature. In diamond anvil cells, devices that squeeze materials between two diamonds to generate extreme pressures, researchers have tested how carbon behaves under conditions similar to those deep inside large rocky exoplanets. At pressures of tens of kilobars and temperatures above 1,500 degrees Celsius, 2,700 degrees Fahrenheit, graphite begins to turn to diamond, just as theory predicts. In more recent studies, astronomers used computational models to simulate the evolution of carbon-rich disks. When the C/O ratio is greater than 1, silicates become unstable, while carbides remain solid. Over millions of years, as planetesimals merge and differentiate, the carbon segregates downward, forming vast, glittering interiors. In 2012, researchers from Yale University, including Niku Madhusudan, published a landmark paper suggesting that 55 Cancri E, the nearby super-Earth, might be composed largely of diamond and graphite. Their models showed that the planet's mass and radius could only be explained if its bulk composition was rich in carbon rather than oxygen. It was a thrilling notion, an entire planet, potentially 1/3 diamond by mass. But, as often happens in science, the story grew more complicated. Later observations by the Spitzer Space Telescope and JWST revealed hints of volatile gases, perhaps silicates, perhaps carbon dioxide, suggesting that 55 Cancri might not be a pure diamond world after all, but something in between. Still, even if this particular example falls short, the physics behind the idea remains sound. Carbon worlds may not be rare, they may simply be hard to see. Their black, non-reflective surfaces would absorb light, making them nearly invisible against the dark of space. Only through their mass, density, and spectral fingerprints can we infer what they're made of. Yet perhaps the most profound insight from all this isn't just that diamond planets can exist, but that they must. Because the universe doesn't favour oxygen, it doesn't favour carbon. It simply builds with whatever it has at hand. Near carbon stars, the chemistry tilts one way. Near oxygen-rich stars, it tilts another. Each stellar generation leaves a different inheritance for the worlds that follow. Some stars seed blue planets with oceans and weather. Others create black planets of crystal and carbide. Both are natural. Both are inevitable. It's a quiet reminder that even the rarest wonders, a planet made of diamond, for instance, are not miracles in the universe's eyes. They're consequences of ratios, temperatures, and time. If we could witness this process from afar, the birth of a diamond world, it would look almost serene. A red carbon star glowing dimly against the void, surrounded by a disk of dark dust. Inside that disk, countless particles collide, merging into embryos of rock and crystal. Occasionally, a flash, a collision big enough to vaporize whole regions, but most of the time, only quiet motion. Over millions of years, the fragments grow heavy enough to pull themselves into spheres. The heat of formation melts their interiors. Carbon, squeezed by gravity, begins to reorganize itself. Layer by layer, the planet crystallizes. If you could see through its surface, you'd watch the slow metamorphosis. Graphite rearranging into diamond, silicon carbide forming glittering seams, metals sinking to the core. And then, one day, the process ends. The planet cools. The disk dissipates. The star stabilizes. And in the stillness that follows, a new world glints faintly in the dark, unseen, unvisited, perhaps eternal. The irony, of course, is that diamond, the hardest material in the universe, begins as something fragile, a whisper of dust, a flake of soot from a dying star. Every planet, every gemstone, every mountain starts that way, as chaos made patient by time. Even Earth, in its earliest days, was a churning sphere of molten rock, endlessly bombarded by debris. The difference is that our chemistry leaned toward oxygen, and so we cooled into a world of silicate stone and water. If the recipe had been different, if our sun had been a little more carbon-rich, the earth beneath our feet might not be blue and green, but black and silver. Our continents would shimmer like obsidian under a dimmer sky. Our mountains would be faceted cliffs of crystal, and our atmosphere, if we had one, might smell faintly of metal and methane. In another universe, we might have walked upon a diamond earth, beautiful, eternal, and utterly lifeless. That's the quiet truth behind the physics of formation. Worlds are not chosen, they are simply forged by chemistry, gravity, and chance. The cosmos doesn't sculpt with intention, it sculpts with ratios, and sometimes those ratios produce something extraordinary. A planet that glitters in the dark, born from the dust of dying stars. If you could slice a diamond planet open, if you could look deep inside its body the way we peer into Earth's mantle, you'd find a structure both familiar and profoundly alien. It would have layers, like our own planet, crust, mantle, core, a rhythm written into all worlds shaped by gravity. But in a carbon planet, each layer would tell a different story. Where Earth's interior is sculpted by silicates and molten rock, a diamond planet's heart would be a monument to carbon, dense, dark, and crystalline. Its beauty would be invisible from the surface, hidden beneath kilometers of unbroken black crust. Yet if you could somehow see it, you would be staring into an abyss of light, a planet with a heart that refracts eternity. Let's start at the surface, the quiet skin of this alien world. The outermost layer would likely be graphite, a thin crust perhaps a few kilometers, a few miles thick. On Earth, graphite is soft, something we crush into pencils. But here, under low gravity and constant bombardment from micrometeorites, it would form a glassy shell. Its surface would glimmer in dull reflection, like oil on metal. In places, impacts could fracture the crust, exposing gleaming veins of deeper material. Below this graphite crust, the transition zone begins, a realm where the weight of the planet starts to change matter itself. As depth increases, so does pressure. At around 45 to 60 kilobars, graphite begins to compress into a denser form. Its atoms, once arranged in soft sheets, reorganize into the rigid lattice of diamond. This transition point, called the graphite-diamond boundary, would be one of the most dramatic in any planetary interior. A few dozen kilometers, a few dozen miles down, the planet would transform from a dark, brittle crust into a mantle made almost entirely of solid diamond. And not just a few scattered veins, but entire layers of it, stretching thousands of kilometers, thousands of miles, deep. If Earth's mantle is a sea of silicate rock, then a carbon planet's mantle would be an ocean of crystal, dense, unyielding and dazzling beyond imagination. To appreciate how extraordinary that is, let's compare it to home. Earth's mantle begins roughly 35 kilometers, 22 miles below the surface and extends down to about 2,900 kilometers, 1,800 miles. At the bottom, where the mantle meets the outer core, pressures reach around 1.4 million kilobars or 360 gigapascals, enough to crush any known material into exotic states of matter. Diamond, on Earth, is stable only within a narrow window, between roughly 45 and 60 kilobars, at temperatures above 1,000 degrees Celsius, 1,830 degrees Fahrenheit. Below that pressure, it relaxes back into graphite. Above it, it can melt or transform into even denser structures. But in a carbon planet, that window doesn't close. The entire interior sits within the conditions needed for diamond to form and remain stable. It's as if the whole planet is a single vast pressure chamber, a crucible turning graphite into gem. That means a diamond planet wouldn't just have diamond at its core, it is the diamond, layer after layer of compressed carbon, crystallized by gravity itself. Inside this mantle, conditions would vary with depth. Near the surface, diamond crystals might be relatively small, a fine granular structure. Deeper down, where pressure and temperature soar, the crystals could grow massive, merging into enormous continuous domains. Not the glittering gems of earthly jewelry, but something purer, seamless crystal extending for kilometers. At even greater depths, heat becomes the key sculptor. During formation, collisions between planetesimals and the decay of radioactive elements would have raised internal temperatures to thousands of degrees. At around 2,000 degrees Celsius, 3,600 degrees Fahrenheit, diamond begins to behave differently, not as a rigid solid, but as a material capable of slow, plastic flow. It wouldn't melt, but it would deform over geologic time, allowing the mantle to convect gently, redistributing heat outward. So the planet wouldn't be entirely static. It would breathe slowly. Pressure gradients would drive sluggish motions deep within the diamond, like the quiet churning of ice in a glacier. But instead of water, the movement would be carbon under a sunless sky. Beneath this crystalline mantle lies the core, the heaviest and most mysterious layer of all. In a carbon world, metals like iron and nickel would sink early during formation, just as they did on Earth. But with carbon so abundant, these metals might absorb it into their structures, forming iron carbide alloys, extremely dense metallic substances far harder than the core materials of our own planet. This core might make up a third of the planet's total mass, surrounded by a shell of pure diamond thousands of kilometers thick. At the very center, pressures could exceed those found at Earth's core, reaching beyond 360 gigapascals, a realm where even diamond's atomic structure could start to change. Some models suggest that under such extreme conditions, carbon could form new exotic phases, possibly metallic carbon, a hypothetical form that conducts electricity like copper but retains diamond strength. If such materials exist, they could make a carbon planet's core unlike anything else. Not molten, not solid, but something in between. A metallic diamond heart, humming with trapped heat and ancient pressure. How heavy would such a world be? That depends on its composition and size, but let's imagine a planet similar to Earth in radius. Diamond is denser than silicate rock, but less dense than metals. Its average density is about 3.5 grams per cubic centimetre, compared to Earth's mean density of 5.5 grams per cubic centimetre. That means a pure diamond planet the size of Earth would actually be lighter, perhaps 60 to 70% of our planet's mass. But carbon planets aren't made of diamond alone. Their cores contain iron alloys, which add weight. If roughly 1/3 of the planet's mass were metallic, the total density might rise close to Earth's, maybe slightly below. A carbon planet, twice Earth's radius, however, could easily outweigh our own by several times. Its immense layers of diamond adding pressure and mass beyond anything we've experienced. And that pressure, that silent compression of carbon, would be the defining feature of the world. To visualize this pressure, it helps to imagine what 1 square centimeter of diamond planet mantle would experience. For every kilometer, 0.6 miles, you descend, the pressure increases by roughly 1,000 kilobars. By the time you reach a depth of 2,000 kilometers, 1,200 miles, you're looking at 2 billion times the atmospheric pressure at sea level. At that depth, light itself would bend under stress. Sound would travel differently, faster, denser, almost metallic in tone. If you could knock on the wall of such a world, it would ring like a bell of crystal. Geologically, a diamond planet would be remarkably stable. Earth's surface changes constantly, shifting plates, earthquakes, volcanoes, all driven by the slow convection of its silicate mantle. But diamond conducts heat too efficiently. It would drain thermal gradients before convection could take hold. The result, a planet that cooled early and stayed still. No continents sliding, no volcanoes, no magnetic reversals, just silence. Over time, its surface might accumulate a thin layer of dust, debris from asteroid impacts or carbon-rich winds, but the planet itself would barely change for billions of years. Where Earth's mountains rise and erode, a diamond planet would stand forever, razor-edged, immortal sculptures carved by gravity and chance. To understand how this would look from space, picture the Earth in shadow, the moonlit side of the world where oceans fade into darkness. Now remove the atmosphere, the oceans, the weather, all the fragile features of life, and leave only the bones. That is what a diamond planet would be. The bones of creation, stripped bare and gleaming. The crust, black and smooth. The mantle, dense and clear. The core, molten iron and carbide under unimaginable pressure. A perfect geologic equation, carbon plus time equals eternity. But such perfection has a cost. Without tectonics or volcanism, a diamond planet would have no way to recycle carbon or generate complex chemistry at the surface. No fresh minerals rising from below, no outgassing to create an atmosphere. It would be beautiful, yes, but chemically sterile. The same element that forms the backbone of life here would render the planet lifeless there. It's a poetic irony. The same carbon that makes us soft and warm-blooded can also make a planet hard and eternal. And yet, despite its stillness, the physics of such a world would be dynamic in another sense. Deep below the surface, in its diamond mantle, radioactive decay would continue to generate heat. But instead of bursting out as magma or volcanoes, that energy would slowly radiate away, a whisper of warmth escaping through solid crystal. If you could measure the heat flow from such a world, it might be astonishingly low, a few tenths of a watt per square meter, barely enough to melt frost. Its light, if any, would come not from fire, but from reflection. A carbon planet close to its star might gleam faintly with metallic hues, gold, silver, obsidian, depending on its surface composition. From a distance, it might look like a dark mirror drifting through space, catching starlight only at its edges. There's something quietly tragic about it too. A diamond is forever, they say, but forever can also mean frozen. A diamond planet would never shift, never erode, never change. It would exist in perfect equilibrium, timeless, flawless, and utterly empty. And perhaps that's what makes it so compelling to us, the contrast between its beauty and its silence. We live on a world defined by motion, oceans, weather, erosion, life. A diamond planet is its opposite, a monument to stillness, carved in pressure and sealed by time. Yet in that stillness there's a kind of peace, a reminder that not every form of perfection needs to breathe, that even in the absence of life, the universe finds ways to create wonder. The physics of it all, the transformation of graphite to diamond, is almost elegant in its simplicity. Add pressure, add heat, weight, that's all the cosmos ever does. It's the same process that happens on Earth, deep below our feet, where graphite-rich pockets are compressed by tectonic collisions. But here, it happens on a scale so vast that no single diamond could ever be held or even seen. It would stretch from horizon to horizon, an ocean of carbon crystallized by gravity itself. If the night sky hides any true jewels, they are not in our jewelry stores. They are in these silent planets turning slowly in the dark, their interiors shimmering unseen. And somewhere among them, perhaps, is one still young, still forming, its crust thin, its interior glowing faintly from the heat of compression. A planet whose heart is still becoming diamond. For billions of years it will cool, harden and fade, until nothing stirs within it but the faint tremor of passing meteors. Then, one day, it will be as silent as stone, a finished gem alone in the void. That is the destiny of every carbon world, to begin in fire and end in crystal. A transformation not of magic, but of mathematics, the poetry of pressure written across the face of the cosmos. For most of human history, diamonds came from the ground, hidden deep beneath mountains, born of heat and pressure we could only imagine. Now the search for diamonds has moved outward, beyond continents, beyond planets, into the dark space between stars, and somewhere out there, glittering unseen, there may be entire worlds made of diamond. Of all the thousands of exoplanets discovered so far, a few stand out as mysterious, dense, and strangely bright. Worlds that don't quite fit into any familiar category. Some of them orbit stars so rich in carbon that their chemistry could rewrite the rules of planetary formation. These are the real candidates, the places where theory might just meet reality. Among them, one name has become almost mythic in astronomy circles, 55 Cancri e. It orbits a star just 8.6 light-years away, one of the nearest multi-planet systems to our own. The host star, 55 Cancri A, is a quiet, sun-like yellow dwarf, slightly older than our Sun. Around it, 5 known planets circle in orbits tighter than Mercury's, and one of them, the innermost, is extraordinary. 55 Cancri E is what astronomers call a super-Earth, a rocky planet about twice the diameter of Earth and 8 times as massive. That means gravity there would be crushing. A person weighing 70 kilograms, 154 pounds, on Earth would feel over half a ton pressing down on their feet. But it's not the weight that makes this planet remarkable, it's what it might be made of. When scientists first measured its mass and radius in the early 2000s, the numbers didn't quite add up. Its density seemed too high for a silicate world like ours, but not high enough to be a planet made purely of iron. Something in between, something unusual, had to be hiding beneath the surface. At the same time, astronomers studying the chemical makeup of its host star noticed something intriguing. 55 Cancri A appeared to be unusually rich in carbon relative to oxygen. That detail changed everything. In 2012, a team of researchers led by Niku Madhusudan at Yale University proposed that 55 Cancri E might be a carbon planet, a world whose crust and mantle are made largely of diamond and graphite rather than silicate rock. If true, it would mean that a third of the planet's mass, roughly the equivalent of 3 Earths' worth of diamond, could be locked inside its mantle. Imagine that for a moment, a world the size of Earth, with a mantle made of diamond stretching thousands of kilometers, thousands of miles, below the surface. At first, the scientific community was captivated. A diamond planet wasn't just a headline, it was a window into the cosmic diversity of matter. It suggested that our universe might hold worlds sculpted by entirely different chemistries, black, gleaming planets orbiting close to their stars, their surfaces glowing with heat, their interiors glittering with crystal. But like all discoveries that sound too perfect, the story became more complicated the closer we looked. 55 Cancri E is a brutal place. It orbits so close to its star that a year lasts less than 18 hours. Its surface temperature likely exceeds 2,400 degrees Celsius, 4,350 degrees Fahrenheit, hot enough to melt steel or even some rocks. At that proximity, the planet is tidally locked, meaning one side always faces the star while the other remains in darkness. The day side bakes under perpetual fire, while the night side may cool enough for gases to condense and form temporary mineral clouds. For years, telescopes like Spitzer and Hubble struggled to make sense of the planet's strange, fluctuating brightness. Infrared observations revealed changes that suggested molten lava flows or volcanic outgassing. Others showed hints of a thin atmosphere, or perhaps no atmosphere at all. The carbon planet hypothesis was beautiful but fragile. Subsequent measurements of the star's spectrum revised its carbon to oxygen ratio downward. Maybe it wasn't so carbon-rich after all. Maybe 55 Cancri A wasn't a diamond world, but a silicate planet cloaked in superheated minerals, an Earth-like world pushed far past the limits of survival. Still, the data never fully ruled out the carbon idea. Because 55 Cancri E remains an enigma. Its density, temperature, and reflectivity don't quite fit any known model. The James Webb Space Telescope, JWST, launched in 2021, has already turned its gaze toward this world. In its infrared vision, JWST can detect the faint glow of molecules, carbon dioxide, methane, carbon monoxide, each leaving distinct fingerprints in the light that passes through or reflects off the planet's atmosphere. And while the early results lean toward a rocky world with silicate vapor in the air, a faint hint of carbon still lingers. Perhaps the surface is molten rock, but the interior, unseen, silent, could still hide diamond within. In the end, 55 Cancri A remains the closest thing we have to a confirmed diamond planet. Not because we know it is one, but because we can't yet prove it isn't. But it isn't alone. There are other candidates, stranger, larger, and more distant, whose chemistry hints at the same possibility. One of them is HD 149026b, a planet so dense and compact that it puzzled astronomers from the moment it was found. It's a gas giant, roughly the size of Saturn, but with more than twice its mass. Its core is enormous, far larger than theory predicted for planets of its kind. When it was first measured in 2005, scientists estimated that its central core might contain 70 to 80 Earth masses of heavy elements, metals, silicates, and possibly carbon compounds. That kind of composition made it a potential hybrid, a planet that began as a rocky, carbon-rich world before drawing in thick layers of gas. In other words, a diamond planet that grew too big for its own brilliance. The host star, HD 149026, also shows signs of chemical enrichment, an above-average abundance of heavy elements, possibly including carbon. If that star's disk once had a C/O ratio above 1, its inner planets could have formed from carbon-heavy materials before the gas giant swept through. Unlike 55 Cancri E, HD 149026b is too hot and too thickly veiled in atmosphere for us to see its surface. but its high density and temperature, reaching nearly 1,700 degrees Celsius, 3,100 degrees Fahrenheit, make it one of the best candidates for a carbon core giant. If it truly formed in a carbon-rich disk, its interior could still contain vast layers of diamond compressed beneath oceans of metallic hydrogen. Another intriguing candidate is WASP-12b, a planet that almost defies classification. It orbits so close to its parent star that it's being torn apart by gravity, its atmosphere stretched into a glowing stream that spirals into the star itself. This planet is huge, about 40% larger than Jupiter, yet much less dense, swollen by heat to a bloated state. But what drew astronomers' attention was the composition of its star. In 2011, researchers discovered that WASP-12's host star appeared to have a carbon-to-oxygen ratio greater than 1, the first clear sign of a star that might spawn carbon worlds. If the star's chemistry reflects that of its planetary system, then WASP-12b could be a gas giant with carbon-rich layers, perhaps with diamond or carbide forming deep in its core under pressures far beyond human comprehension. Even more fascinating, the planet's atmosphere shows traces of methane, CH4, and carbon monoxide, CO, clear indicators of carbon chemistry dominating oxygen. These molecules absorb light at specific infrared wavelengths, and both Hubble and Spitzer detected them in abundance. To many astronomers, WASP-12b became the first observational hint that carbon-rich planets were not just theoretical. If the chemistry of its skies reflects the material of its interior, then somewhere beneath its glowing stormy clouds might lie a carbon heart, a diamond giant slowly falling apart. The challenge with confirming any of these worlds, though, lies in the nature of distance itself. We can't touch them, we can't send probes. We can only watch how their starlight changes. When a planet passes in front of its star, a transit, a fraction of the star's light filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of light, leaving faint imprints, absorption lines, that act as fingerprints. By studying those patterns, astronomers can infer what chemicals are present. But there's a catch. The signals are faint, sometimes just a few parts in a million, and they depend on countless variables: temperature, cloud cover, viewing angle, even magnetic fields. It's a bit like trying to guess what a candle smells like by watching its flame through fog. That's why the existence of true diamond planets remains unconfirmed. Our instruments can tell us a planet's size, its mass, and sometimes its atmosphere, but not what lies beneath. We can estimate a world's density, but density alone can't reveal its chemistry. A silicate planet with a massive iron core could weigh the same as a carbon planet with a lighter core and thicker mantle. Until we can read the light coming directly from the planet's surface, not just the atmosphere, the truth will remain hidden beneath layers of inference. The James Webb Space Telescope has begun to change that. With its advanced infrared spectrometers, JWST can detect fainter signals than any telescope before it, the whisper of heat from planets that would otherwise vanish into darkness. Already, Webb's early data have hinted at more chemical diversity than we ever expected. Some hot exoplanets show carbon monoxide where we expected water vapor. Others show carbon dioxide without trace oxygen, a possible sign of carbon-rich formation environments, and a few exhibit thermal signatures that don't match silicate worlds at all. It's too soon to call any of them diamond planets, but the groundwork is being laid. Within the next decade, missions like Ariel, the atmospheric remote sensing infrared exoplanet large survey, will measure the spectra of hundreds of exoplanet atmospheres, searching for those telltale carbon fingerprints. And perhaps among them will be a planet whose chemistry leaves no doubt, where carbon outnumbers oxygen and diamonds are not jewels, but geology. Still, even when that day comes, we may never truly see such a world, not with our eyes, not even with the clearest telescope. A diamond planet would not shine like a gemstone. It would be dark, nearly black, absorbing light rather than scattering it. Diamond itself is transparent, but mixed with graphite and carbide, it becomes opaque, swallowing the light of its star. From space, it might resemble a shadow drifting across the void, featureless, silent, invisible except for the thin line of starlight reflecting off its edge. A world of diamond, hidden in darkness. And maybe that's fitting. After all, the most beautiful things in the universe are rarely the ones that draw attention. 55 Cancri E HD 149026B WASP 12B. Each one is a hint, a whisper, that somewhere, among the thousands of worlds we found, there are planets of crystal orbiting unseen. They remind us that the cosmos is vast enough to hold every possibility, that even the improbable can exist given enough time and gravity. And perhaps one day, long after we're gone, some distant civilization will land on one of them. Their instruments will dig into the crust, their sensors will echo through the mantle, and they'll find what we can only imagine now. A planet glittering from the inside out. For now, though, these diamond worlds remain among astronomy's most tantalizing mysteries, half proven, half dream. And maybe that's exactly where they belong, because in the end, what makes them beautiful isn't their certainty, it's their possibility. Imagine standing beneath a sky that has never known blue. Above you, there are no clouds, no ozone haze, no sunlight diffused into colour. Only the raw glow of a nearby star, burning white through a thin metallic atmosphere. The air, if you could call it that, shimmers faintly with carbon dust and hydrocarbon mist. The ground beneath your boots reflects the light like dark glass, and when you look to the horizon, the landscape seems carved not by wind or water, but by pressure and crystallization, jagged ridges of carbide rock catching the faint glint of the sun like blades. This is what an alien world of diamond might look like. A planet sculpted not by erosion, but by chemistry, where the familiar cycle of rock, rain, and river has been replaced by something stranger, the slow, silent dance of carbon, metal, and light. The surface of a carbon planet would be a study in extremes. The crust, formed from graphite and silicon carbide, would be dark, almost mirror-like in places, absorbing nearly all light. Under a carbon-rich star, illumination would feel dim and directional, as if the entire world existed in perpetual twilight. If the planet orbited close to its star, as many of our known candidates do, the heat would be relentless. Temperatures could reach 1,500 degrees Celsius, 2,700 degrees Fahrenheit, or more on the day side, enough to melt some of the surface minerals into viscous, reflective pools. From orbit, these patches might gleam faintly like mercury, giving the planet a flickering metallic sheen. Step too close, and you'd find the soil isn't soil at all, but sheets of graphite, cracked and fused into plates of dark crystal. Your footprints wouldn't last here, they'd vanish instantly, as electrostatic dust shifted underfoot and settled again like silk. The air, thin and dense at once, might shimmer with hydrocarbon vapours, methane, acetylene, and carbon monoxide, molecules that would condense into strange, oily hazes as night fell. Instead of water vapour forming clouds, carbon compounds would dominate the weather, creating streaks of bronze and black across the sky. In some regions, depending on temperature and pressure, droplets of liquid hydrocarbons, similar to what we see on Saturn's moon Titan, could fall as metallic rain, staining the surface in glossy streaks before evaporating back into vapour. Imagine rain that smells like gasoline, shining silver in the starlight, pooling for minutes before dissolving into smoke. The terrain itself would be alien beyond description. On Earth, landscapes are shaped by the flow of water and the slow collapse of rock. But here, erosion would come not from water or wind, but from temperature, from the planet's own fluctuations between night and day. If the planet were tidally locked, one hemisphere would face the star forever, baking under perpetual fire, while the other would lie in eternal shadow. Between them, a twilight band, the Terminator Zone. might offer the closest thing to balance, a region where heat and cold meet, forming bizarre crystalline weather patterns. On the day side, molten carbon compounds could bubble up from fissures, spreading into reflective planes that harden as they cool. On the night side, methane frost and frozen carbon dioxide might blanket the surface in glittering grey. The boundary between them, the half-light region, could be a world of contrast. Glowing diamond ridges catching faint starlight, shadowed valleys lined with black graphite dust, and skies pulsing with distant lightning, thin bluish arcs sparking through carbon haze. The mountains here would not look like Earth's either. They would rise sharp and sheer, built from silicon carbide, a material so hard it rivals diamond itself. Their slopes would gleam under the dim light, their peaks fractured into jagged crystalline spires. In the heat of day, the upper layers might glow faintly red as the minerals absorb solar radiation. By night, they would radiate the stored heat slowly, casting a soft infrared shimmer visible only to instruments. If the planet had a thin atmosphere, one with enough pressure to scatter light, the sky might take on peculiar colours. Instead of blue, it could appear bronze, copper, or violet, depending on the amount of carbon haze suspended in the air. A high concentration of fine graphite dust could make sunsets appear metallic, a dark gold glow fading into black. And in the absence of water vapour, the stars would shine almost painfully bright, cold, sharp points in a sky stripped of diffusion. There would be no moonlight, no clouds, no softness, only contrast, blinding light, and infinite shadow. In some places, particularly near the substellar point, the region directly facing the star, the surface might melt completely, forming lava seas of molten carbide and carbon. These seas wouldn't look like lava on Earth. They would be darker, thicker, metallic, like pools of liquid steel, sluggish and heavy. When the light hit them at a low angle, they would reflect the star in dazzling ribbons, turning the landscape into a mirror of fire. At the edges of these seas, where heat begins to drop, strange crystalline formations could appear, carbon frost forming over molten rock, diamond grains crystallizing as gases escape into cooler regions. In a way, these places might resemble frozen oceans of black glass, solidifying in slow motion under the light of an alien sun. Imagine standing at the edge of one of those seas. You'd see a horizon that gleams like metal, trembling with convection. You'd feel heat rising through the soles of your boots, each breath tasting faintly of burnt metal and ozone. The light would refract strangely, scattering into hues your eyes couldn't quite name, deep red at the edges, shifting to indigo and white near the centre. Even the concept of day would feel distorted. With no atmosphere thick enough to diffuse light, shadows would fall razor sharp, and colours would seem almost exaggerated, too pure to be real. If you moved toward the night side, the ground beneath you would change. The air would thin, the temperature would drop sharply, perhaps hundreds of degrees colder, plunging below minus 150 degrees Celsius, minus 238 degrees Fahrenheit. Any vapours that existed near the dayside would condense into frost, coating the rocks in fragile layers of frozen hydrocarbons. The ground might crack underfoot, brittle from rapid cooling, producing faint crystalline echoes, the sound of carbon contracting in silence. Light itself would behave differently here. On Earth, light scatters through air molecules, giving us soft gradients and gentle transitions. But on a carbon planet, light would move across the surface like a blade, reflected and refracted by crystal lattices, absorbed by graphite, split by diamond. Imagine a landscape that seems to shimmer even when perfectly still, not because it moves, but because light cannot decide how to behave on it. In the heat of the day, reflections from diamond layers just beneath the surface might create spectral halos, faint rainbows arcing across black plains. To the human eye, it would look like a mirage, but it would be real, born from the bending of light inside a planet-sized gemstone. From orbit, these worlds might look paradoxical. dark as soot from a distance, but dazzling up close. Diamond, despite its clarity, reflects most incoming light internally, trapping it, bending it, scattering it deep inside, so a diamond planet's surface would not shine like jewellery. It would glow from within, faintly, as if lit by embers. And yet, even in this harsh and lifeless beauty, there might be complexity. Depending on the planet's distance from its star and the gases that remain in its atmosphere, hydrocarbon seas could exist. Black oceans of liquid methane, ethane, or acetylene stretching for hundreds of kilometres, hundreds of miles. These seas would be denser than water, smoother than oil, and eerily reflective. A single gust of wind could send ripples across the surface, distorting the reflection of the star above into molten patterns of gold and onyx. Lightning could flash in the distance, thin, violet streaks arcing from cloud to cloud, igniting pockets of methane into brief, ghostly flames before fading back into silence. No life would exist there, not in any form we recognize, but chemistry would never stop. Everywhere, reactions would continue in slow motion, gases bonding and breaking, carbon rearranging itself endlessly as it has for billions of years. For a planet rich in carbon, even rain could be metallic. At certain pressures and temperatures, carbon and silicon could vaporize and recondense in the upper atmosphere, forming droplets of molten silicon carbide, tiny grains that fall like dust, glowing faintly as they descend. As they strike the surface, they would cool and harden into microscopic crystals, adding layer upon layer to the crust. Over eons, the planet's surface would thicken, turning darker and smoother, a slow polishing process that leaves behind an obsidian world. And somewhere far below, beneath those smooth plains, the real beauty hides. A mantle of diamond, miles deep, glowing faintly from the trapped heat of the core. That heat might escape through cracks and vents, not as fiery eruptions like on Earth, but as silent fountains of gas and plasma, shimmering with static light. You might walk for days across that world and never hear a single sound, only the soft hum of static charge and the occasional hiss of sublimating carbon frost. The air would be too thin to carry echoes, too heavy to breathe. Even the sound of your own steps would feel muted, absorbed by graphite dust. To human eyes, it would be hauntingly beautiful, but to the universe, it would be ordinary. There's something humbling about that a world of diamond and crystal could exist without witnesses, shining unseen in the dark, that the cosmos can sculpt a planet of flawless carbon and then leave it drifting, cold and indifferent. We tend to imagine beauty as something intentional, as if the universe created such places for us to marvel at. But in truth, they exist because physics leaves no other choice. Given the right conditions, the right ratios, the right pressures, the right star, a carbon planet must form, and when it does, it will look nothing like home. It will be a place where black skies shimmer with bronze haze, where metallic rain falls into hydrocarbon seas, and where diamond mountains rise in silence under a dead sun. From a distance, a carbon planet would appear almost invisible, a faint silhouette against the light of its star. But through a telescope tuned to the right wavelength, you might catch a glimmer, not of reflection, but of heat. A dull, red glow from the dayside, fading into cold shadow on the other. A world that neither shines nor burns, but simply endures. And in that endurance, there's something profound. Because even in the emptiest places, in the dark, airless gulfs between the stars, the universe finds ways to create beauty, not for us, not for anyone, just because it can. We often say that life, as we know it, is carbon-based. Our bodies, our food, our very thoughts are built on long chains of carbon atoms linked with oxygen, hydrogen and nitrogen, a chemistry so intricate it feels almost miraculous. But on a carbon planet, that same element, carbon, would be abundant to the point of dominance. And that raises a strange question. If carbon builds life here, what happens when there's too much of it? Life needs balance. On Earth, carbon doesn't exist alone. It lives in a complex equilibrium with oxygen, hydrogen, nitrogen, and a dozen trace elements. Oxygen allows for energy transfer. Hydrogen binds molecules into flexible shapes. Nitrogen creates the structure of proteins and DNA. And above all, water acts as a solvent, the great mediator that allows these elements to meet and react. But on a carbon planet, the chemistry would be inverted. Oxygen would be scarce. Carbon would rule everything. The crust, the air, the oceans, if there are any, would be saturated with it. And that means the familiar chemistry of life would break down before it ever began. Imagine standing on such a world, one of those diamond planets locked in eternal day. The ground beneath you is carbon crystal. The air smells faintly of acetylene, methane, and dust. There is no water, no oxygen, no soil as we understand it. Temperatures swing between minus 150 degrees Celsius, minus 238 degrees Fahrenheit on the night side, and 2000 degrees Celsius, 3600 degrees Fahrenheit near the day side. Even in the most temperate regions, if they can be called that, the air is heavy with carbon monoxide, hydrogen cyanide, and other reactive gases. In that kind of environment, water-based life simply couldn't exist. Water would boil away or freeze instantly. Oxygen would be locked in molecules that are far too stable to use as an energy source. Photosynthesis, respiration, even simple metabolism, all impossible. But that doesn't mean chemistry itself would be silent. Astrobiologists have long speculated that if life exists elsewhere, it might not need water or oxygen. It could rely on other solvents, liquids that can dissolve and transport molecules just as water does for us. One candidate is liquid methane. On Saturn's moon Titan, for instance, methane flows like water. Rivers of it carve valleys into the icy crust. Rain made of methane falls from orange clouds. Entire lakes and seas glimmer in the twilight. It's one of the few places in the solar system where we've actually observed stable liquids on the surface. And Titan's environment is, in some ways, a preview of what a cold carbon planet might offer. Temperatures there hover around minus 180 degrees Celsius, minus 292 degrees Fahrenheit. Unimaginably cold, but perfect for methane and ethane to remain liquid. Its atmosphere is thick with organic molecules, long, complex chains of carbon and hydrogen that form naturally in sunlight. Some scientists think Titan could host exotic forms of chemistry, slow, methane-based reactions that might one day give rise to life, or at least mimic it. Such life, if it exists, wouldn't breathe oxygen or drink water. It might metabolize hydrogen or acetylene instead, using surface chemistry we can barely imagine. If Titan can do this on a small, frigid moon, then perhaps somewhere among the stars, a carbon planet could too. But there's a limit. For methane-based life to exist, temperatures must be low, between roughly minus 200 degrees Celsius and minus 100 degrees Celsius, minus 328 degrees Fahrenheit, and minus 148 degrees Fahrenheit. Above that range, methane becomes unstable, evaporating and breaking apart into simpler molecules. Most carbon planets we've found orbit close to their stars, where surface temperatures are far too hot for such chemistry. Instead of methane seas, they have carbon vapor and molten carbides. Instead of frost, they have plasma. Those worlds are beautiful, but sterile, their heat sterilizing any chance of complex molecules forming or surviving. However, not all carbon planets need to be close to their stars. Some could drift farther out, where temperatures drop low enough for gases to condense. Imagine a cold carbon planet orbiting a dim red dwarf star, its surface locked in twilight, its atmosphere thick with methane and hydrogen. There, in the shadows, droplets of hydrocarbon rain could pool into shallow lakes, and chemical reactions could take place over millions of years. Perhaps not life as we know it, not with cells or DNA, but something slower, quieter, patterns of chemistry that adapt, replicate, and evolve in their own way. It would be a different kind of biology, one not driven by speed or heat, but by endurance. Astrobiologists call this the alternative biochemistry hypothesis. the idea that life doesn't have to follow our formula. It could be silicon-based instead of carbon-based, or it could exist in solvents other than water, ammonia, methane, sulfuric acid, even liquid carbon dioxide. Silicon is often mentioned because it sits just below carbon in the periodic table. It can form 4 chemical bonds, just like carbon, and create long chains, the backbone of complex molecules. But there's a problem. Silicon's bonds are heavier and more rigid. They don't form the same variety of stable, flexible molecules that carbon does. And when exposed to oxygen, silicon quickly turns into silica, sand. So while silicon chemistry works in theory, in practice, it's far less adaptable than carbon. Hydrocarbon chemistry, on the other hand, is both simpler and more flexible. Even in a carbon-dominated world with little oxygen, there would be no shortage of hydrocarbons: methane, ethane, acetylene, benzene, and countless others. Under the right temperature and pressure, these molecules can polymerize, linking together into complex structures, much like the amino acids of earthly life. So if life did exist on a carbon world, it might not breathe oxygen or exhale carbon dioxide. It might live in methane lakes, feeding on acetylene and releasing hydrogen as a byproduct. Its cells might not be made of membranes like ours, but of waxy hydrocarbon shells, and its pace of existence would be glacial, chemical reactions taking hours, days, or even centuries to complete. Such beings, if they could think, would perceive time differently, their world unfolding in the slow rhythm of freezing rain and drifting methane clouds. There's something poetic about that idea, that even on a world so hostile to us, life might find a way to bloom in the shadows. But the odds are small. A carbon planet's environment is unforgiving. Without oxygen, it's difficult to create energy gradients, the fundamental difference between food and waste that powers metabolism. Without water, it's hard to maintain molecular mobility, the constant dance of atoms that makes biochemistry work. Even with hydrocarbons as a substitute, the reaction rates would be incredibly slow, so if life ever arose on such a planet, it would be minimal, perhaps existing only as surface films, chemical colonies, or drifting molecular networks, more like coral reefs of chemistry than living organisms. And maybe that's the point. Maybe the universe doesn't need every world to teem with life. Maybe some worlds exist to show what life isn't, how easily the spark can be extinguished when the balance shifts. There's one last possibility though, a haunting one. A carbon planet that forms near a star might begin as molten and lifeless, but as the star ages and dims, the planet could cool. Over billions of years, temperatures might drop low enough for gases to condense, forming methane oceans and carbon frost. If water-bearing comets ever struck its surface, even briefly, they might create localized reactions, tiny bursts of chemistry that last for seconds before evaporating. In that fragile window, before the water boils away, complex organic molecules could form, the same building blocks that gave rise to life on Earth. Not enough to create biology, but enough to seed the surface with potential, a kind of chemical memory of what might have been. In that sense, even a dead carbon planet could be fertile in its own way, not alive, but rich in the ingredients of life. The same carbon that denies life in one form makes it possible in another. The same diamond crust that seals its silence could, under the right conditions, hold the spark of organic chemistry inside. It's almost as if the universe leaves every door open, even the ones that lead nowhere. So, could a carbon planet host life? Probably not life as we know it, but perhaps something simpler, or slower, or stranger. Something that drifts through methane seas, metabolizing heat and light in ways our biology could never imagine. And even if not, the idea itself changes how we see life, not as a miracle confined to one chemistry, but as a pattern that could arise whenever the universe gives it a chance. Because if there's one thing carbon teaches us, it's versatility. It can be soft as graphite, clear as diamond, invisible as gas, or solid as stone. It can build bodies or planets, forests or gemstones. It can sparkle in the sunlight, or sleep forever in the dark. And somewhere between those two extremes, between life and silence, lies the mystery of every world that carbon touches. Imagine walking across the surface of a diamond planet, black skies above you, diamond crust beneath your feet, and realizing that the very ground you stand on would be considered priceless on Earth. Every step would shatter our sense of value, because here, diamonds aren't treasures, they're terrain. What would precious even mean on a world made of jewels? On Earth, rarity defines worth. A diamond's value doesn't come from what it is, carbon, but from what it isn't, common. It's not the element itself we admire, but the conditions required to form it, the heat, the pressure, the deep time. We see beauty in what's difficult to obtain. But in the cosmos, rarity is relative. In the furnace of the stars, carbon isn't rare at all. It's one of the most abundant elements in the universe. Every star, every nebula, every planet, all are dusted with it. The same element that forms our jewellery, our pencils, and our DNA floats freely in space, carried on solar winds, scattered by supernovae. It's an irony so vast it almost feels cosmic in itself. The universe produces in abundance what we spend fortunes to unearth. On a carbon planet, diamonds would be as common as sand. A mountain made of diamond would be no more remarkable than a hill made of granite. The idea of polishing a stone for beauty would seem absurd. Why polish what surrounds you endlessly in every direction? In that sense, a diamond planet is not just a scientific curiosity, it's a mirror, one that reflects the strange way humans assign meaning. We live on a world where scarcity shapes our desires. Gold, platinum, gemstones, they've all been elevated to symbols of success, permanence, or love, not because of their intrinsic properties, but because there isn't much of them to go around. But if we could hold a world of diamonds in our hands, that illusion would dissolve. Value, it turns out, is just an agreement between beings with limited perspective. In the context of the cosmos, our treasures are trivial, and that realization is quietly liberating. In 2012, when researchers first suggested that 55 Cancri E might be a diamond planet, the headlines erupted with excitement. The public reaction wasn't about astrophysics, it was about money. How much would it be worth? How many carats could a planet hold? If we could mine it, what would it do to the global economy? But of course, that question misses the point entirely. If diamonds were everywhere, they'd be worth nothing. Economics collapses when abundance replaces scarcity. In a way, the diamond planet became the ultimate thought experiment, a reminder that value depends not on substance, but on context. A diamond on Earth can buy a house. On 55 Cancri E, you couldn't trade one for a breath of air. This irony reveals something profound about our species. We measure meaning by what's hard to reach, but the universe doesn't. To the cosmos, carbon is simply carbon. It doesn't care if it's arranged as graphite, diamond, or gas. It doesn't assign beauty or worth. It just exists in the form that physics demands under a given pressure and temperature. And maybe that's the quiet lesson hiding in these glittering worlds. That preciousness is not a universal truth, but a human invention. It's not the first time science has reshaped what we call valuable. There was a time when salt was worth more than gold, when a simple mineral could decide the fate of empires. Then came iron, oil, uranium, each in its era, each worshipped for its scarcity, its power, its promise. But every time humanity expanded its understanding of the world, what we valued shifted. When we learned to synthesize diamonds, they became less sacred. When we found new materials, new energies, we replaced one symbol of wealth with another. And now, as we look beyond Earth, we face the ultimate devaluation, the universe itself. Out there, every element we prize exists in unimaginable abundance. Gold may glimmer in our vaults, but entire neutron star collisions forge it by the ton. Oceans of methane flow on Titan. Mountains of ice rise on Pluto. And perhaps, in some distant orbit, a planet of diamond turns silently in the dark. Richer than any kingdom, yet utterly empty. In a cosmic sense, our economy is built on ignorance. The moment we see the universe as it is, value becomes impossible to measure, but that doesn't make it meaningless. If anything, it makes our sense of worth more intimate, because once you strip away scarcity, all that's left is meaning, the kind we create ourselves. A diamond in a shop window is not rare in the universe, but it's rare to us. It represents love, permanence, or the weight of memory. That meaning is not in the atom, it's in the story we attach to it. In that way, human value becomes something even grander than cosmic value. We give emotion to matter. We make symbols out of dust. We turn simple carbon into metaphors for eternity. And in doing so, we add something to the universe that physics alone cannot: significance. Perhaps that's why the idea of diamond planets fascinates us so much. Not because we want to own them, though some probably do, but because they make us question what ownership even means. If a billion-carat planet exists, then diamonds lose their magic. But maybe, in that loss, something deeper emerges. Maybe it reminds us that beauty doesn't need to be rare to matter. A single snowflake, a shell, or a grain of sand can hold the same wonder as a planet of crystal, if we learn to see it that way. The cosmos is abundant beyond measure, but meaning is still scarce. That's what makes it precious. The concept of cosmic economics isn't about money, it's about perspective. When you stand on Earth and look up, you see stars and think of distance. But from those stars, Earth is just another point of light, a speck with oceans, air, and thinking beings who assign value to shiny stones. It's a humbling thought. We are the only known creatures in the universe who care that diamonds sparkle. Perhaps that's our role, to be the universe's consciousness of itself, to notice beauty even when it's everywhere. To say, this matters even when the cosmos doesn't. And if that's true, then a diamond planet doesn't diminish beauty, it magnifies it, because it shows how fragile our definitions are, and how easily wonder returns when we let them go. In a strange way, carbon worlds reveal the ultimate equality of matter. Everything, from the carbon in our breath to the carbon in a star's heart, is part of the same endless cycle. On one planet, that carbon forms life. On another, it becomes stone. On yet another, it becomes light. The universe is an economy without money, an exchange of energy, structure, and time, and every element plays its part. When you think of it that way, a diamond planet isn't rich at all. It's simply efficient, a place where carbon found its most stable form and stayed there forever. Value, as we understand it, exists only here, on this small, imperfect planet where rarity still means something, and where we can still marvel at a gemstone for its scarcity rather than its chemistry. So perhaps the real treasure isn't the diamond planet itself, but the insight it gives us. That meaning is not in matter, but in mind. The cosmos doesn't know the difference between a pebble and a diamond, but we do. We're the ones who name, who feel, who seek. And maybe that's why, even in a universe of infinite abundance, wonder never runs out. Because no matter how vast or empty it becomes, we're still here, assigning value, making stories, finding beauty in the things that don't need it. A diamond planet might be priceless, but the ability to care about it, that's the rarest thing in the universe. Carbon is the quiet architect of the universe. It doesn't shine like hydrogen, it doesn't collapse like iron, it doesn't roar like fusion, but it builds. Wherever carbon drifts, structure follows. It's strange to think that this humble element, number 6 on the periodic table, shapes everything from the black dust of space to the breath of living creatures. Yet it does. In the grand cycles of galaxies and stars, carbon is both a product and a creator, forged in death, but endlessly giving rise to life. Every atom of carbon in your body was born in a star. Billions of years ago, when the universe was still young, there were no carbon atoms at all. The early cosmos was a sea of hydrogen and helium, light, simple gases created in the first minutes after the Big Bang. There were no solids, no chemistry, no life, only the potential for all of it. Then came the stars. They were the universe's first engines, colossal spheres of nuclear fire, collapsing under their own gravity, burning hydrogen into helium in their cores. For millions of years they shone, grew, and aged, until finally they began to run out of fuel. In their exhaustion, something miraculous happened. The heat and pressure in their cores climbed high enough to fuse helium into carbon, 3 helium nuclei merging in a process called the triple alpha reaction. It's one of the most elegant reactions in nature, simple, inevitable, and profoundly consequential. Without it, there would be no solid worlds, no organic molecules, no life. When those stars finally died, they cast their carbon into space, not gently, but in magnificent explosions. Supernovae, stellar winds, planetary nebulae, all of them spreading dust into the dark, each grain a tiny seed of carbon waiting to be gathered again by gravity. That dust is the raw material of everything that came after. Every rocky planet, every comet, every molecule of sugar or leaf or bone, all descended from those ashes. In astronomy, this recycling of matter is called the galactic life cycle. Stars are born, they live, they die, and their deaths enrich the galaxy with heavy elements. From that debris, new stars and planets form. In time, those too will die, scattering their enriched contents further, continuing the cycle. Carbon is one of the main currencies in that cosmic economy. It's forged in one generation of stars, carried by the next, and eventually woven into the fabric of worlds and living things. When astronomers look at galaxies across billions of light years, they can actually trace carbon's spread over time, a slow brightening in the infrared spectrum as more and more stars contribute their dust to the cosmic medium. The Milky Way, our own galaxy, is in the middle of this evolution, rich in carbon, active with star formation, and filled with clouds of molecular gas that glow faintly with organic compounds. If you could see the Milky Way through infrared eyes, you'd see it breathing, carbon and hydrogen forming new molecules in the dark, swirling through nebulae like incense smoke. One of the most beautiful sights in the night sky is a dying star called a carbon star, an old, swollen giant nearing the end of its life. These stars have spent billions of years quietly burning helium into carbon deep within their cores. As they age, convection carries that carbon outward, mixing it into their outer layers. The star reddens, cools, and begins to shed its atmosphere into space. What it releases is not mere gas, but dust, tiny grains of graphite and soot drifting outward in a slow, glowing wind. In infrared images, these stars look like embers, fading but radiant, each surrounded by a halo of material that will one day become planets. It's poetic, really. Stars dying by giving everything away. Their light dims, but their legacy expands. These carbon stars are the factories of the universe's most complex molecules. In their dusty shells, carbon atoms combine into long chains and rings, precursors of organic chemistry. Some of these molecules are astonishingly complex: formaldehyde, acetylene, even simple sugars. And when this dust mingles with interstellar hydrogen, it forms compounds that resemble the first ingredients of life. Every organic molecule we know, from alcohols to amino acids, starts in places like this. The universe doesn't make life deliberately, it just keeps making chemistry. Given enough time, chemistry starts to resemble life. Astronomers have found evidence of organic molecules in the most unlikely places, in the icy comets of our solar system, in the atmosphere of Titan, in meteorites that have fallen to Earth carrying amino acids older than our planet. Even in the vast cold spaces between stars, the so-called interstellar medium, telescopes detect faint spectral lines from complex molecules like methane, ethane, and formaldehyde drifting freely through the void. To think that such molecules exist out there, suspended in the vacuum, billions of kilometers, billions of miles, from any planet, is quietly humbling. It means that the universe's chemistry is patient, that the foundations of life are not fragile, but resilient and ubiquitous. Carbon's genius lies in its flexibility, It can bond to almost anything. 4 connections at once, forming chains, rings, lattices, or sheets. It can be gas, liquid or solid, graphite or diamond, soot or sugar. It can hold energy in its bonds, release it in reactions, or store it for eons. It's the Lego of the cosmos, endlessly adaptable, endlessly creative. Everywhere we look, carbon is both the sculptor and the storyteller. In star-forming regions like the Orion Nebula, its dust absorbs and re-emits light, painting the clouds in hues of red and orange. In the thin halos around dying stars, it carries heat outward, cooling the stellar core and ensuring that the next generation of stars will form at all. In young planetary systems, it seeds the building blocks of life before the planets themselves are fully formed. And perhaps most beautifully, carbon never stops moving. Once freed from a star, it drifts through interstellar space, sometimes for millions of years. Eventually, gravity pulls it into a new nebula, where it joins with oxygen and hydrogen to form molecules again. It may fall into a planet, dissolve in an ocean, or spiral into another star to begin the process anew. In that sense, carbon is immortal. The atoms in your body, in your bones, your blood, your breath, were once parts of other worlds. They may have belonged to long-dead stars, to planets that no longer exist, even to life that lived and perished before Earth was born. When you exhale, those carbon atoms leave your body and return to the atmosphere, to plants, to soil, to oceans, and in the grander scale, some will one day leave Earth entirely, drifting into space, waiting again for gravity to call them home. We are quite literally the universe reassembling itself into consciousness, carbon thinking about carbon. It's no wonder that when scientists find carbon in distant systems, we take notice. It's not just an element, it's a signature, a hint that the story of chemistry there might be following the same melody as ours. When telescopes detect carbon monoxide or methane in an exoplanet's atmosphere, we lean closer, as if the universe had whispered a familiar word in another language. Carbon connects us. It's the thread that runs from the first stars to the last breath of every living thing. And in the end, it's also what remains. Because when a star dies, when its light finally fades and its core collapses, carbon endures. It's one of the last elements to survive the fire, one of the first to be reborn in the dust. That's why the galaxy glows in infrared. It's not just starlight. It's the warmth of carbon dust, still carrying the memory of every star that ever lived. To look at a diamond planet or a graphite asteroid, or even a grain of interstellar soot, is to look at the same substance that makes up us, rearranged, redefined, but still recognizable. The same bonds that give carbon life also give it endurance. It is, in a way, the universe's handwriting. Elegant, simple, unending. From the death of stars to the birth of life, from dust to consciousness, carbon tells one continuous story, that creation and destruction are not opposites, but partners, 2 sides of the same cosmic process. And as long as stars continue to burn, that story will never stop being written. Before we ever looked up at the stars for meaning, we looked down into the earth, and there, hidden in the dark, we found light. For thousands of years, diamonds have been our most enduring symbol of eternity, fragments of purity torn from the depths, shaped by fire and pressure, and brought into the sun. They were the first material to make people believe that perfection could exist in solid form, that something flawless could survive the chaos of the world. But now we know there are entire planets made of them, and somehow that makes them even more mysterious. On Earth, the story of the diamond begins in myth long before it begins in geology. Ancient civilizations believed they were pieces of fallen stars, tears of the gods, or splinters of eternal light trapped in stone. In Sanskrit, the word for diamond, vajra, also means thunderbolt, a weapon of divine power. The Greeks thought diamonds were the crystallized breath of celestial beings. To the Romans, they were talismans of courage, believed to protect warriors in battle. The first recorded diamonds came from India, mined from riverbeds around 2,500 years ago. They weren't cut or polished as we do today. They were worn in their raw, natural form, cloudy, irregular, almost unremarkable by modern standards. But their rarity and their sparkle in candlelight made them unlike anything else. Even then, people sensed there was something unnatural about them, a strength that defied explanation. They were the hardest substance anyone had ever encountered. They couldn't be scratched, couldn't be burned, couldn't be broken. In a world made of fragile things, that alone made them divine. As trade spread across continents, diamonds became currency, status, and myth combined. By the Middle Ages, they were the chosen jewels of kings and queens, not just for their beauty, but for their symbolism. They represented permanence in a transient world. A marriage sealed with a diamond was meant to last forever, just as the stone itself would never decay. That association, diamond as eternity, still lingers in the way we use them today. We don't buy them for function. We buy them for promise. They're meant to embody something that endures when everything else fades. And yet, if eternity is what diamonds represent, then the cosmos is full of them. Entire planets spin through the dark, their mantles solid crystal, their mountains eternal. If only we could see them, we might realize that eternity is not rare, it's the rule. Modern science stripped away the myth, but not the fascination. In 1797, the English chemist Smithson Tennant proved that diamonds were made of nothing more than carbon, the same element found in soot, wood, and living tissue. He burned a diamond in pure oxygen and found that the only product was carbon dioxide. The revelation was shocking. The purest, hardest, most brilliant substance on Earth was made of the same thing that blackened a chimney. It was a humbling discovery. It suggested that perfection wasn't a matter of ingredients, but of arrangement, that beauty could arise simply from atoms organized in the right pattern. It was nature's reminder that form, not substance, creates meaning, and that idea, that carbon could be both ash and diamond depending on circumstance, became a quiet metaphor for human experience itself. We are, after all, made of the same element. The carbon in our bodies could one day crystallize into diamond under enough pressure. In a sense, the universe has already shown us that we and the stones we prize share the same ancestry. Our obsession with diamonds, though, grew beyond science. In the 20th century, marketing turned them into the ultimate symbol of love. The famous phrase, "a diamond is forever," coined in 1947, tied emotion to geology, making an ancient rock the emblem of human connection. A geological process became a story, and a story became an economy. But when we discovered that there might be planets made of diamond, that story changed. Suddenly, what we had considered rare became cosmic dust. The stone we use to symbolize eternal love was now something the universe mass produces without care or witness. And that realization forces us to ask, if the universe can make entire planets of diamond, why do we still find them special? The answer, perhaps, is that diamonds aren't precious because they're rare, but because of what they mean to us. On Earth, diamonds are born deep underground, roughly 150 to 200 kilometers, about 90 to 120 miles beneath our feet, where pressures exceed 45 kilobars and temperatures climb above 1,000 degrees Celsius, 1,830 degrees Fahrenheit. They take millions of years to form, rising to the surface only through volcanic eruptions. When you hold one, you're holding a piece of the Earth's mantle, a relic of a time before life began. That story of transformation through pressure resonates deeply with us. It's a story of endurance, of surviving heat and darkness to become something luminous. It's why diamonds became metaphors for strength and purity, not because they're perfect, but because they come from imperfection. So when we look at diamond planets, perhaps the awe isn't about wealth or rarity, but about scale. They remind us that the universe performs the same miracle everywhere, turning simple carbon into crystal under the right conditions. that the process that happens under our feet happens also in the hearts of worlds light years away. The cosmos doesn't need poetry to describe it, yet it creates poetry in its physics. Throughout history, humanity has used diamonds as symbols of what we long for most: permanence, clarity, truth. We see eternity in their geometry, divinity in their symmetry. But the universe, indifferent and vast, shows us that eternity is common. What's rare isn't the diamond, it's the fleeting warmth of life that admires it. If 1 billion carats glitter unseen beneath alien skies, what makes the one in your hand special? It's not its brilliance or its purity. It's you, the act of seeing it, admiring it, giving it meaning. That's what transforms carbon into treasure. In that sense, every diamond on Earth is an act of perspective. It's not the universe's perfection we're admiring, but our own capacity to find beauty in it. So perhaps discovering diamond planets doesn't humble the symbol, it expands it. It turns the diamond from a luxury into a lesson. That what we cherish isn't defined by the cosmos, but by consciousness. That value comes from context, and that even in a universe where diamonds are common, love, meaning, and curiosity remain rare. We're drawn to diamonds because they survive, because they remind us that something can last. But they also remind us of what can't. Their light will outlive every civilization that ever adored them. When our species is gone, when our sun fades and our world cools, the diamonds in Earth's mantle will remain, silent, perfect, unknowing. They will endure, not because they are eternal, but because they don't need to remember. Perhaps that's what the universe is really teaching us through these diamond worlds, that endurance and awareness are opposites, and we can't have both. We shine, briefly, like light across a gemstone's edge. We're the momentary reflection, not the stone itself. And yet, that fleeting light, that consciousness, is what gives the universe meaning at all. A diamond planet may last forever, but it will never understand its own beauty. Only a fragile mind here on a small blue world can do that. So, the next time you see a diamond, imagine it multiplied 1 billion-fold, stretched across an entire planet. Imagine a world of crystal turning silently in the dark, then look back at the tiny one between your fingers. It may be small, but it carries within it the same story, the same atoms, the same pressures, the same light. The difference is that here it's loved, and in that single fact lies a truth greater than eternity. Somewhere out there, far beyond our reach, a planet made of diamond turns slowly in the dark. It doesn't sparkle, doesn't glint. There's no sunbeam to catch its edges, no observer to name its light. It simply exists, silent, perfect, and unseen. We imagine it shining, but the truth is quieter. Its brilliance is buried under its own weight, locked inside, reflecting nothing, revealing nothing. And still, it glows, faintly, invisibly, with the memory of the star that made it. A world of endless crystal drifting through the night of space. An ocean of diamond under skies of black. Beautiful, not because it gleams, but because it doesn't need to. We spend our lives searching for beauty, chasing it through objects and places and faces, forgetting that the universe makes it everywhere, effortlessly. It hides it in dust, in stone, in silence, even in darkness. If we could look at the cosmos, not with our eyes, but with patience, we'd see that beauty isn't rare. It's our gaze that's small. There are worlds made of diamond, and stars that breathe carbon into the void. There are clouds of sugar drifting through nebulae, frozen oceans of methane, mountains of sapphire, and black holes bending light like glass. The universe doesn't create beauty sparingly, it does it constantly. We're simply lucky enough to have evolved the sense to notice. Every discovery we make, every exoplanet, every molecule, every faint shimmer in the dark, humbles us a little more. It reminds us that our stories, our values, our treasures, all belong to a single corner of a single world. And yet, within that smallness, there's wonder, because we're made of the same material we study. The carbon that built those diamond planets also built us. It thinks through us, dreams through us, looks back at itself through our eyes. In a way, Every human thought is a diamond, pressure and time made conscious. The sparkle of a mind against the backdrop of infinity. Maybe that's what these distant planets are here to teach us. That beauty doesn't need to be seen to exist. That value isn't measured in rarity, but in recognition. That the universe doesn't create meaning, it offers possibility. Meaning is what we bring to it when we look up. So we look through telescopes, through equations, through imagination. We peer into the dark and ask, again and again, what's out there? And the cosmos answers, patiently, in its quiet language of light and time. Everything, everything, and more than you'll ever see. It's comforting somehow to think that even when we're gone, when our world fades, when our cities crumble and our oceans still, there will still be planets of diamond turning in the dark, still stars burning carbon into dust, still beauty, endless and unaware. It doesn't need us to witness it, but we need it to remind us that we belong to something vast and calm and eternal. So as the fire crackles beside you and the night folds softly around your thoughts, remember this. Out there, the universe glitters, not with gold or jewels, but with patience. With the slow, endless transformation of simple elements into impossible worlds. With the quiet alchemy that turns dust into stars and stars into life. Maybe beauty was never meant to be rare. Maybe it's meant to be everywhere. And we are meant to be the ones who finally notice. Thank you for listening. Thank you for drifting through the dark with me, for following this small thread of thought across light years and lifetimes. As you rest now, let the idea settle quietly that somewhere beyond sight, the universe keeps shimmering, calm, infinite, and full of light. Close your eyes. The stars will take care of the rest.